Yeah, continue.
Yes, yes, yes. Nice to have you, sir. We'll just wait for a couple of minutes for some more to join, then we will start.
Okay, sure. So continue.
Yes, sir.
May I know tentatively what is the background of the audience so that accordingly I can.
So mostly the audience who are joining here are BTech undergraduates.
Okay.
Few MTech undergraduates are also there, and we also have research scholars present with us.
Okay.
And mostly everyone is from the technical background of like any branch of electrical science. It can be CS or ECE or Triple E,
Okay.
but
But
like all in this related
but
background only.
okay. But mostly it is undergraduate student, right?
Yeah, mostly undergraduate. Some MTech can
Some.
join.
Okay.
They have
Okay.
not yet joined, I see, and
Okay.
some research scholars are also there.
Okay. Fine.
Okay, I think let us start, and people will, they will join. Uh, like they are joining again. So yeah, we can start. So I hope I'm audible, right? Okay. So good evening, everyone who are present here, and a very warm evening on behalf of IEEE Computer Society Student Branch Chapter. So today we are gathered here to hear a lecture on harnessing edge intelligence for video services by Professor Subhadeep Bhattapyal. He is the assistant professor from the Department of Computer Science and Engineering in IT Durgapur. And I am Kunta Sarkar. I am currently a PhD research scholar from IIT Kharagpur, and I will be the host of today's event. And first of all, I would like to welcome all of you, and specifically Professor Bhattabyal for finding your time to give us the lecture over here. So, a warm welcome from our CSSBC towards you. Thank you so much. Uh, Let me, before beginning, I would like to introduce our esteemed speaker first. So, Professor Subhadeep Bhattabyal is currently serving as the assistant professor from the Department of Computer Science and Engineering in NIT Durgapur. He holds a PhD in engineering from Jadavpur University. Prior to this, he was the assistant professor from the Department of Computer Science and Information Systems, BITS Pilani in Hyderabad. The main research interest of Dr. Butterball lies in the areas of adaptive video streaming, intelligent caching at the edge, several types of optimization problems in cellular networks, and similar kind QoS provisioning, QoE provisioning, and similar kinds of work. He has had over several publications in reputed international journals and conferences throughout his academic career. Dr. Butterbell has received the Visiting Scientist Fellowship under the TÜBİTAK program of the government of Turkey, and he has also received the SERB Sire Fellowship for visiting the University of Carleton in Canada. So, before we begin, a few general instructions to the audiences. So during the talk, I would like to request all of you to please keep yourself muted, and please wait till the end to ask your questions. There will be a separate Q&A session at the end. An attendance sheet will be distributed at the later part of the talk. Please note your attendance over there. And in the meantime, if you have any query or issue, you may type in the chat box and we will try to resolve those. And at the end, we will be taking a group screenshot of the event. So if possible, please turn on your camera when asked to, so that we can take a group screenshot. So with this, I would again like to welcome Dr. Subodhi Butterbell to this particular event. And without waiting further, let us start the stream. Let us start our talk for today. Over to you, Professor.
Okay, so thank you, Kontio, for the introduction. So, uh,
Let me just unshare my screen so that you can share.
yes.
Yes.
So I hope my screen is visible.
Yes, yes, the screen is visible. Thank you.
Okay. Okay, so today's topic is on harnessing edge intelligence for video services. Right. So I came to know that most of you are undergraduate students. So I will try to keep it very brief and very basics and fundamental, so that whatever you have covered in your undergraduate, especially your networking area. And then some part of caching techniques. I think most of you have done caching in your computer organization or computer architecture, right? So those fundamentals will be very helpful in understanding today's talk. Okay. Apart from that, I will give you some additional information regarding what are video services and how edge intelligence helps in delivery of video services. Right. So these are the agendas, but typically I will try to address the first three or four topics. Right. Rest of the topics I will be just highlighting so that most of you can understand. Now, so today, we are currently residing in the era of smart devices, right? All of us have at least one or two mobile devices, tabs, right? And then we have, uh, in few years we'll look at other smart devices like smart specs like Google specs, right? And all these things. And there are a number of surveillance cameras all around us, right? Traffic surveillance cameras, drone surveillance cameras. So today we are residing in the age of you know videos, proliferation of devices which generate videos and which receive videos. Okay. So every day trillions of data are downloaded from different servers. It may be some YouTube server, it may be Netflix server, it may be different kinds of other video on demand servers, store devices, and also live streaming of videos. For example, now itself we are doing some live streaming of videos on YouTube, live streaming on Google Meet, right? So this puts a tremendous pressure on the network, right? When I say network, I typically mean the cellular network, right? Because after all, the backend network is delivered by one or more cellular service providers, right? It may be Airtel, it may be Geo, it may be BSNL, it may be any other telecom service providers. Okay. So to cater to these millions of devices who are downloading very high definition video every second, there is a tremendous pressure on the network to provide these kind of services. Now, why do I say tremendous pressure? Because when 10 years back, we were not very much concerned about the quality of the video, right? So so today, as the cameras are getting improved, the your video quality is getting improved. It is very easy to understand that as the quality gets improved, right, the size of the video will also get increased, right? So previously we had very poor quality video and we were not very concerned about that, as long as the video, uh, we could watch the video. But today, not only we want a continuous streaming of video, but we want very high definition video. For example, if you're watching some movie on your mobile phone, you don't want that movie to be very low quality, right? We want a very high definition video quality. So high definition video quality means, automatically means, that there is the data rate required is very high, right? Because if the data rate is low, either you will receive a very poor quality video, or your video will get buffered every now and that means it will get stuck every now and then, right? So you need to have a tremendous bandwidth, you need to have a tremendous data rate, and millions and millions of such devices are downloading video every second. So you can imagine the amount of bandwidth that the cellular service providers have to deliver or to provide to the customers. So you can see here, I've put here some trends, right? This trend shows a CAGR, which is compounded annual growth of different devices. So first graph on the top left shows how many billions of devices. So you can see that almost 30 billion devices are today are there, and you can see the growth from 2018 to 2023. Out of these 30 million devices, how many of them are internet users? So you can see out of these, there are number of connections. So on the top right, you can see that almost there is a 19% increase in number of connections. Now when I say connections, it means different kinds of connections. It may be Wi-Fi connection, it may be a cellular connection, it may be some other kind of any other kind of connections, right? So you can see out of these 30 million, almost 15 million devices, 15 billion devices they are always connected to each other, either to Wi-Fi, either among themselves, or to a cellular service provider. Out of these, almost 5.5 or 5.3 billion devices are internet users, right? And you can see on the top, so on the bottom right, you can see what are the different kinds of applications. So you can see 5G applications are there, IoT applications are there, then ultra reliable low latency applications, which typically refer to the video applications, video services. So all these are different applications which are very in very need of edge computing, the edge computing paradigm. Now, what is edge computing paradigm? I will come to that. Right, so this shows how many exabytes of data are downloaded per month, and on the right hand side you can see what are the different applications. So it can be gaming application, it can be file sharing application, web, right, video on demand, and then internet video, right? And out of these, how many of, so out of these, so the last one, internet video, is the maximum. It contributes to the maximum amount of data that is downloaded every month. And out of these internet video, how much of these are video surveillance, right? The bottom graph shows the video surveillance, live internet video, right, video on demand, and then short form internet video on demand, right? So from these figures, from these graphs, you can easily you can easily know, or you can easily understand what is the tremendous pressure that the cellular service providers are meeting. Now there are number of ways in which you can improve a cellular service, right? So previously we had 2G, then 2.5G, 3G, 4G, right? For short period of time, 4.5G, and then now we have 5G that we have arrived. By the time 5G arrived, several other countries are already experimenting with 6G and 6.5G, right? And some of the countries have already deployed that. Right? Now, what is this G, and what is the actual philosophy behind this G? So it is just simply an asymptotic increase in the amount of data rate or the data rate delivery to the end user equipment. Now, this increase in data rate depends upon number of factors, right? It's not very easy to understand, but some of the factors are improvement in modulation and coding scheme. That is a physical layer part of the network, right? Those who have already studied the networking mm, course, they can understand that there are, five layers, right, in the TCP/IP protocol, where we have the physical layer, then we have the data link layer, network layer, and then finally the TCP layer and the application layer, right? So the physical layer, in the physical layer, there are improvements in coding technique, there are improvements in the modulation technique, which contributes to the improvement in the data rate. Then we have algorithms and schemes, improvements in the MAC layer or the data link layer, which again contributes partially to the improvement in data rate. Then there is some improvement in the networking layer. So in each layer there are several improvements that each generation of network are taking place, which is actually increasing. It's an asymptotic in. Why do I say it's an asymptotic increase? Like, it's not that previously it was in 4G it was, let's say, 100 mbps, now it's 110 mbps. It's not like, the service providers will not spend millions and millions of dollars in just to increase 10 MB speed from 100 to 110 mbps, right? So it's an asymptotic. So probably it was 100 mbps, now it's at least 1 gbps, right? It should be at least 1 G. So there should be a significant improvement. There should be a significant improvement in the data rate, given that the number of devices are increasing at an exponential rate, right? So that is the scalability part, that is the asymptotic part. That means even though there is an increase in the number of devices, even though there is an increase in the number of user equipments that are putting tremendous pressure on the network service providers, still how we can improve the data rate. Now, why do I improve that? Why do I want to improve the data rate? As I said, to improve the quality of data service, to improve the quality of video service, right? That means we want to watch very high definition video without the video getting stuck, right? Now, you will understand that there are, so one of the very simplest way of improving the data rate is just to increase the number of base stations, right? So uh, a very fundamental thing is that, let's say there are millions of users in a particular city, right? So if there is only one base station, you can imagine the amount of data rate that a particular user will get, right? Now, instead of putting just one base station, if you increase the number of base stations in a given area, right? So that will significantly improve the data rate. That is the simplest technique, right? Just increase the number of base stations, right? And then do some kind of designing, and different things are there, right? I'm not going into that. And you have to, of course, you have to place those base stations at some strategic positions, right? You cannot place them anywhere you like, right? So you simply increase the number of base stations and you will get a better data rate, right? But that is a very simple technique, but that doesn't always work. So there are several reasons for that. Okay. There can be interference, there can be there can be you know the issue of backhaul bandwidth, right? So etc. So there are a number of reasons for that, right? So simply increasing the base stations always doesn't work. So what is the other option that we have? Okay. So I'll give you a simple example. So suppose you are downloading a video, right? So where does that video come from? It comes from some server, right? Either that, let's say if you're downloading video, watching a video on YouTube, that video will come either from some YouTube server, which is located, some thousands of kilometers apart. It may be in some US, or it may be somewhere in India, but it's, of course, it's not near uh, to your location from where you are watching your video, right? So I think you have already studied that if when you click on a video, what is the time that is taken to when the videos to start? So you have you know what's the delay, right? So the delay typically consists of two components, two basic components. One is your propagation delay and one is your transmission delay, right? So you know what is a transmission delay, right? So it's simply L by R, where L is your size of your data and the R is the data rate, right? Plus the propagation time is the distance between the sender and the receiver divided by the speed of your signal, right? So that is the delivery time of your video, right, from your server. So that is the total time, right? Transmission time plus propagation time, right? On top of that, so let's say, so this is a very ideal case, right? This is a very, very ideal case where delay is equals to transmission speed plus the propagation speed. But there are some additional delays to that as well. So there can be processing delays, right? So there can be some acknowledgement delays. That means you are delivering a data, but the data arrives, so there is an error in the data arrival. That means the data is not correctly received, so the sender has to again resend the data, right? So automatic repeat request, right? ARQ process, right? So if a data is delivered in an erroneous manner, it has to be resent by the sender, right? Or there can be some forward error correction, FEC. That means there are some redundant packets will be there, and then you apply some coding techniques, and then you recover the error message which was received without resending the data once more, right? So you try to recover the data from some duplicate or from some redundant packets, right? So that's called the forward error correction, and there are a number of techniques for that, right? So it's not as simple as that. It's only a transmission data and the propagation data. So there are a number of factors, or there are some additional delay components which prevents the application from starting on time, right? So even if you get the give the best data rate, even there will be significant delay. So what is the other option? So suppose that you have a base station. So ultimately you are downloading your video through the nearest access point, right? Which is, so I'm assuming that you are downloading from, you are connected to your the nearest base station, and you are downloading it from cellular network. You are not connected to Wi-Fi. You are not connected to any of your college network. I'm assuming that you are downloading it from directly from the cellular. That means you have turned on your uh, you know your mobile data, and you are downloading the video, okay, from your mobile device, okay. So what is the best so now, instead of pulling the data from the server, what is the other option we have? We can cache the data at the base station. That means, let's say this video has already been downloaded by somebody, right? Of your friend or somebody has already downloaded this data, and the data has arrived through the base station. And let's say this video is a very, very popular video, right? I'm assuming that this is a popular video. So why not store that video into the nearest access point, which in this case is my base station, right? Cellular device. So which component will which component of delay will this get reduced? Of course, the propagation time, because now the distance is not kilometers, millions and millions of kilometers, but it is a very one or two few kilometers, right? So that will significantly reduce my propagation delay, right? What other delay can it reduce? So it can also reduce the probability of error, right? So if it also reduces the probability of error, right? I mean, it may not be always so, but reducing the distance, of course, reduces the probability of error. So if it reduces the probability of error, of course, your processing time will also get reduced, okay. So this concept of fetching the data uh, without going into the source, without going into the source or without going into the cloud, is called the concept of edge. Now, in network, you must have studied that there are different parts of network, right? So there is the core network, right, where you have different routers. Then you have the edge network, and then you have the access network, and then you have finally your user equipment, right? So these are the different parts of your network, how the packet travels from the source to the destination. So if we have certain devices at the edge of the network, that means just a one step, uh, you know you know just one hop to the user equipment, and if we can fetch the data from that edge equipment, right, so that will significantly reduce my um, you know that will significantly reduce my delay, right? So that is just one of the advantages of using edge device. Now, what is edge computing? So that is a caching at the edge. Now, what is edge computing? Now, instead of caching, what I can do is, suppose I want to do some kind of computation. Let's say I want to do some kind of processing. Let's say I want to do some kind of video analytics, right? So you must have seen there are thousands of video surveillance cameras that are placed on the roadside, right? And those cameras, what are they doing? They are recording the video of the traffic, and then they are sending that video to some kind of data center, where if any kind of event happens, that video is processed, and then necessary action is taken. For example, if there is an accident, right, first the surveillance video records the video, it sends to some kind of control center. The control center analyzes the video, it detects that some kind of accident has taken place, and then whoever has made the accident or violated some traffic rule, accordingly that vehicle is detected and segregated from the traffic, right? So that is the general trend, but that process again takes a lot of time, right? So by the time that vehicle is detected, you have to do the computing, video is transferred from the camera, you do the processing, and then we detect the video by the time that vehicle would have already left the scene, right? So to reduce the processing time, what we can do, that if we have some kind of computing or processing element already in the surveillance camera itself, right? So we can do the processing in the camera, and then we can send the signal directly to some nearby kiosk or to some nearby police, and that police can take the measure and immediately capture or segregate the vehicle from the traffic, right? So that computing, that means where carrying out the computing as close as possible to the source of the data. So what is the source of the data in this case? The source of the data is the traffic surveillance, right? So the video camera which are placed at the roadside, and if we can do the processing at the camera itself without sending the video to the kiosk or without sending the video to the data center, right, we can take the steps very quickly. So that computing, if the computing happens near the source of the data, that is called the edge computing, right? So what does this guarantee? That is fast data processing, right? It reduces transmission cost. Of course, you can understand that transmitting the video from the video surveillance camera to the data center, that also has an additional cost, right? So that also takes some kind of delay, or that also takes some kind of latency, and the response time will be huge, right? So this, if we can process the data near the source, that will reduce my latency and the response time, right? So this is a pictorial representation of edge computing. So you can see here that what are the different advantages. These are the endpoint devices, okay? And basically the idea is to optimize the TCO. So what is the TCO? This is your total cost of ownership, right? Now, very important question is that who will own these edge computing devices, right? So it can be the different service providers, right? Now, if a certain service provider, let's say Airtel or Jio, want to set up an edge device, right, at the base station, the cost of ownership will be has to be borne by the Airtel service provider, right? But what will be the advantage for that? So the advantage will be the improvement in the customer satisfaction, right? So that will tend to generate more revenue. Okay, so if the customers are satisfied, they are able to watch videos, smoothly and in high definition, right? So that will generate more revenues for the service provider. Okay, so in such cases, the total cost of ownership, instead of if the video is fetched from a far away server, and if it is fetched from a nearby caching device, that will of course improve the that will reduce the total cost of ownership, right? So there has to be a trade-off, right? So the trade-off is improvement in customer service at the cost of installation of the edge devices, right? So that is the trade-off. That is the optimization point. So these are the edge characteristics, and as I had already mentioned: low latency, real-time optimized infrastructure, rapid response, right? Massive data storage and movement, data sovereignty, and then enhanced security and data. Of course, security and data privacy is an issue, right? So that is a separate part, right? So I'll not go into the security and data privacy part. So context, sorry, context and location awareness. Now, a very important question is, uh, when we cache a certain content, right? So for example, when we cache a video, where do we cache it, right? So we don't cache it anywhere, right? Certain video have to be cached at a certain location. Why? It depends upon which video is accessed by which population, right? So of course I will not, for example, let's say, we are in West Bengal, right? In a certain location. Of course, we'll, and many of us watch either Bengali videos or some kind of English or Hindi videos, right? So of course, uh, you know, uh, will not be very inclined to watch some non-Indian language videos unless and until it is very popular. I'm assuming that it is not popular. So we never store contents which are not according to our taste, right? So of course we'll not store. So we'll always store contents which are specific to a location, and which is where there's a high probability that that content will be downloaded by many users in that particular locality. Okay. And so we have multi-access networking across large scale and small scale, small size sites, right? And then we have the intelligence, smartness, and then so these are the different characteristics. Zero touch, that means which requires zero maintenance, right? So it should be self-configurable, it should be self-healing, right? So all these characteristics must be there whenever we deploy some kind of edge computing paradigm. So these are the drivers. Why do we need edge computing? To reduce bandwidth, to reduce latency, to optimize the bandwidth, to improve privacy and security, improved connectivity, right? And of course, local dependency. As I said, that caching and computing has to be location specific. Okay. So these are the different implementations, right? I've just taken some contents from the following uh, referral, right? So there are different implementations of edge computing. So there's a fog computing, then there's a multi-access edge computing, and then there's the cloudlet. Okay, so I'm not going into this in detail. Now, what are the typical edge devices? So which devices do we call as the edge devices? So which devices are capable to be called as edge device? Which device are capable of cache devices are capable of computing? So we have two things. One is storage and one is computing. So edge caching and then edge computing. Okay. So of course, base stations, as I had said, and then there can be small cells. So what are small cells? These are, just like a small Wi-Fi device, right? Where it caters to a very small number of users but provides high bandwidth. Okay. Of course, these small cells are very, very close to the user, maybe within 500 meters of range, right? So you can imagine that whatever the access points which are within 500 meters of range, of course it will have a very good bandwidth, of course, and then it will have a very reduced interference, of course. It will have reduced fading, it will have reduced errors, and etc, etc, of course, right? But you must remember that small cells are, at the end, they are served by the base stations, or they are served by some kind of backhaul network. And of course, so the bandwidth of small cells are also limited by the bandwidth of the backhaul, right? But of course, they are also capable of storing the contents. They are also capable of performing some kind of computations. Then we have radio access network for LTE 5G, which are of course the radio access heads for our base stations. Then we have hotspots, typically our Wi-Fi or access points. Then we can have some kind of micro data centers. So these micro data centers can be attached to the base stations. And of course, we have our conventional routers, switches, and access points, right? So these are the typical edge devices which are capable of acting as an edge device. They are capable of storing, and they are also capable of doing some kind of computation. Okay, so these are the different implementation characteristics. Okay, so I'm not going into the architecture of edge computing. So here you can see briefly, here you can see that the cloud layer, right? That means where my data is actually stored. Okay, and then we have the fog layer, which consists of typically our backhaul networks. Then we have the edge layer, where we have our edge gateway, and then finally we have our edge devices, right? So these are the different, layers of our networks. Okay. So here you can see that these are the different device populations at different levels. Okay, so here you can see that the number of edge devices are more compared to the edge server or the edge gateway, and then we have the edge cloud, and then we have the enterprise hybrid cloud. Okay, so these shows the width of this triangle shows the number of devices in terms of millions, how many billions of edge devices are there. Okay. Now, there are two things which are very important when we talk about video services. So one is an edge intelligence and other is an intelligent edge. Now, what is an edge intelligence? Edge intelligence is the realization of intelligent applications with the assistance of edge computing. So suppose there is an edge device, right? So it can be your access point, it can be your base stations. If the intelligence, now how do I measure intelligence, or basically what is an intelligence? When I say that I've deployed some kind of intelligent application, right? So it can be some kind of AI model, it can be some kind of machine learning algorithms, etc., etc., right? So if I have deployed such kind of models in a edge device, I will call that as an intelligent edge. On the other hand, if that those models are residing at the user equipment, either at the user equipment or at the cloud server, but they are getting assisted by some kind of computation which is happening at the edge device, such kind of paradigm we call it as the edge intelligence. So in edge intelligence, we do not deploy the models, the AI models, or some kind of machine intelligent models, uh, uh, machine learning models in the edge device. They are present either at the user equipment or they are present in the remote cloud server. Whereas if we deploy the models in the edge device itself, such kind of edge devices are called the intelligent edge, right? So solving problems of edge computing with AI solutions. What we actually want is a combination of both of these. That means the real power lies when we have edge intelligence that is assisted with an intelligent edge, right? So we want both of them, and that will make our applications more powerful. Now I will go into the video analytics part. So here I've shown a use case where you can see that this is my traffic surveillance. So there are a number of cameras, and this is my base station. Okay, so the surveillance cameras are sending data at regular intervals to the base station, right? And this base station is sending the data to some kind of you know some kind of control, traffic control office. Okay, so where they are getting analyzed. Now instead of analyzing the video at the control center, what we can do is we can place an MEC server at the base station itself, right? Where we have certain kind of applications. For example, let's say some accidents happen. So what we can do is, as soon as an application accident happens, the MEC server, which is aligned with the base station, can immediately detect the event and can take necessary measures. Whereas if it is a regular surveillance without any kind of event, then that video can be transferred to the traffic server, to the control room or control server, right, wherever you want. So here we have deployed some kind of intelligence into the edge device. That means the edge device is analyzing the video, it is detecting some kind of event. If there is an event, it is sending notification to the nearby kiosk to take an immediate action. If there is no event, then the video is transferred for storage into the cloud server, right? So this is one of the application. Then we have the distributed caching, where we can have multiple MEC server. So here you can see we have a low bandwidth and backhaul transport, okay, and we have these different kinds of service providers, right? Service providers means the video service provider. Okay, there can be YouTube, Facebook, and etc. Twitter, okay, and so these are getting stored in the MEC server, right? And only the highly popular videos are getting stored, because you can imagine why only highly popular, because the storage at the MEC server is limited. We cannot, cloud server, MEC server can never replace the cloud server, right? So cloud server is a huge, has a huge storage, right? Whereas this may have storage only of maybe few terabytes or few exabytes, right? So we cannot store the entire, we cannot shift the entire cloud to the MEC server, but we can store few popular videos, so that my maximum, I can maximize my offload probability. Now, what is offload probability? So you have already studied caching in computer organization, right? So what contents do we store in the cache? The contents which have a high temporal locality, the contents which have a high spatial locality, right? So that means the data or the instructions which are getting accessed repeatedly, right? The data and the instructions which are not getting accessed repeatedly, we store it in the main memory, or we store it in the permanent storage, right? So the same concept is applied here. The contents which are highly popular, that means the people who are watching the videos, certain videos are very, very popular and they are being downloaded repeatedly and by multiple devices. So those videos will store it in the MEC server, so that we can improve the delay. That means we can reduce the delay, and also we can improve the hit rate, right? So we use the terminology hit rate in computer organization. In this case, we call it offload probability, okay? So edge intelligence I've already talked about, right? So now I will quickly go into the video services. Now, what are the video services? So video services typically refer to the real-time video streaming, live video analytics, real-time gaming, real-time content dissemination. Now, what are the challenges? The challenges are, the size of the video is the primary challenge, right? So imagine, thousands of users, and they are downloading the video, thousands of video at a given time, right? So as I said, we cannot replace a cloud server with an MEC server, okay? So we have to choose which video to store and how to deliver that video to the user equipment, right? So the challenges are the size of the data, the latency, right? The pattern extraction. As I said, that there is an AI model which detects an event, right? So what kind of pattern or what kind of extraction, what kind of event do you want to extract from a certain video, right? And then we have the I typically refer to the video, the network resource as well as the computing resource. Okay, so computing resource is a challenge. Computing, we cannot place a very high-end computing resource at the edge device. So, right, for example, just imagine a video camera, right? So in video camera, we cannot we cannot attach a very high-end workstation or a very high-end server along with that video camera, right? So that will not only increase the cost, right? So that will also make it very difficult to deploy, right? So we have to provide very limited resources, computing resources. We can attach very limited computing resources to a particular edge device. Okay, so so now why do I want an intelligent caching? So as I said, intelligent caching refers to which devices. That means how do I decide which device to which video to cache and which video to keep at the at the edge into the cloud server. Then we have the intelligent bitrate adaptation, where we refer to the automatic adjustment of the bitrate. That means you must have noticed that when your network conditions are poor, your YouTube application automatically downgrades your video quality. As soon as your bandwidth improves, automatically your YouTube application improves your video quality, right? So how does it do it? How does it how does it do? So the application, the video application or the application which is there on your mobile phone regularly monitors the bandwidth or the status of your network, right? So it prioritizes the the continuous flow of video compared to the quality of the video. So it doesn't want the video to get stuck, right? Because if it wants to deliver a high quality video at a very poor bandwidth, you can immediately your video will get stuck, right? Because your buffer will be empty, and video will get stuck with it. So therefore it downgrades the video quality so that lower bit rate can be supported by the network bandwidth at that given time, right? And then as I defined intelligent offloading, that means how do we offload the data. That means how do we provide the data as close to the data source for analysis and inference. Lastly, I will quickly touch upon the quality of experience, right? So quality of experience is a very important parameter, right? So previously you must have studied quality of service in your networking, right? So quality of service typically refers to different parameters, right? So it can be your delay, it can be your variance in delay, etc., right? Jitter, etc. Whereas quality of experience is a perceptual, or it's a perceptual quality of the service which the service provider is providing it to you, right? What are the parameters? As I said, for video service it is buffering time, stall ratio, stall rate, quality of the video, right? So typically video quality is measured in terms of pixels. That means it can be your 480p, 720p, right? 1080p, 2160p, right? Of course, you can imagine that as the p value of p increases, your quality improves. So 2160 is the ultra high definition video, right? And then we have the high definition video, which is 1080p. Then you have the medium quality video, which is f720p, and then you have the other lower quality video like 480 and 360p, right? Then we have the bitrate switching. So what is bitrate switching? As I was saying, that when your network quality becomes poor, it becomes 720p. As soon as your network quality improves, it immediately becomes 2160p. So this transition of quality is called the bitrate switching. Okay, and then you have the user engagement. That means you see that if the video that is delivered is of high quality, the user will always be attracted to that video and will watch the video for a longer time. If the video that is delivered is of very poor quality, then the user will repeatedly switch from one video to the other. It will not view the complete video at one go, right? So that is called the user engagement. That means for how long the user is watching a given video, right? So that is called the user. So these are all objective metrics. And then you have certain subjective metrics, which is called the mean opinion score. So this mean opinion score is measured through some kind of survey, right? So that is called the subjective metrics. A very important parameter is distortion and stall. So what is distortion? So distortion is how we are deviating from the best quality of the video. So suppose the original video is ultra high definition, that means 2160p, but because of the poor network bandwidth, because of the poor network quality, I am watching the video at 720p, right? So the difference between the original quality and the viewed quality is called the distortion, right? Now it can be due to several parameters. It can be due to network bandwidth. It can be due to poor channel quality, right? There can be a lot of errors, right? So this is called distortion. Now how do we measure distortion? We measure distortion in terms of different mathematical equations. So that is called the PSNR, that means peak signal to noise ratio, video structural similarity index. Then we have the multi-scale structural similarity index, layer-based distortion, right? So now I will quickly go into layer-based distortion. So what is layer? So basically, when multimedia, right, any kind of multimedia is encoded in terms of different layers, right? For example, you must have heard of scalable video coding, right? where we have a base layer that is called the I layer, and then we have the B layer and the P layer that is called the bidirectional predictor layer and the P layer predictor layer, right? So and the video is divided into number of segments, right? So for example, if I say that my video is of, let's say, 60 seconds, right, and each GOP is of 2 seconds, right? Each GOP stands for the group of pictures. So each GOP is of 2 seconds. So I will have 30 such GOPs, right? And what does each GOP consist of? It consists of frames. So if I say that my video is of 30 frames per second, which means that within a GOP, I will have 30 frames. Okay. So what are the different frames? As I was referring, the first frame is called the IDR frame or the I frame. And then we have different kinds of other frames like predicted frame and the bidirectional predicted frame. Okay, so I'm not going into the details of that, right? For that, you need to know details of motion prediction and etc. Different things. Okay, now you can imagine that if I receive only the base layer, that means basically I will receive a video of the lowest quality, right? So assume that my base layer is of 420p or 480p or 720p, and as I keep on adding the layers, my video quality gets improved, right? So that is just an abstract way of thinking. Okay, so that means my base layer, that is my iframe. So basically my iframe is my base layer. So base layer is of, let's say, 480p, and that as I keep on putting the layers, I improve my video quality, right? So you can imagine that if I receive the best quality video, I have received all the layers, right? So assume that, let's say, I have 5 layers, right? Or let's say I have 4 layers. That means 480p, 720p, then on top of that 1080p, and then on top of that, let's say 2160p. So if I receive all the layers, then I will be watching the video in 2160p, 2160p resolution. If I receive only 3 layers, I will be watching the video at 1080p. If I receive only 2 layers, I'll be watching the video at 720p. And if I receive only 1 layer, that means only the I layer, I'll be watching the video at 480p. Right? So depending upon the network condition, right, I will be accordingly receiving the number of layers, right, given certain delay. Okay. Now you can see here is an example. So if my GOP on my video has 5 layers, and if I receive only 3 layers, right, then the distortion is calculated by this equation, Dmax minus the number of layers from I equals to 1 to L. And now there's a product. Why there's a product? Because you see, each layer is dependent upon the previous layer. That means if I don't receive the first layer, I cannot decode the second layer. That means my second layer is dependent upon the first layer. If I don't receive the second layer, I cannot decode the third layer, right? So therefore, to decode the third layer, I must have completely received the first layer and the second layer. Okay, so that's why I put this in this formula, right? So if I receive only the first, it is 1, right? If I receive both, it is 1.1. If I receive 3, it is 1.1.1. And you see, I've received only 3 layers, and I have not received the last 2 layers. So my distortion will be 2. Now this is only for one GOP. Now I can measure the average distortion. So let's say my first GOP will have distortion 2, my second GOP may have distortion 3, my third GOP may have again distortion 2. So after receiving the entire video, I measure what is my average distortion, right? And that is how I can measure the quality of the video, right? So these are the different measures of distortion, right? So this paper was this is the paper which was presented in WCNC in 2020. Right? So I think I will not no more go into this, because let's say a given video, let's say there are a number of small cells, right, under a given base station, and it is not necessary that I store only one content in only one small cell. The same content may be stored in some other small cells, right? But it has to be again strategically cached. So how to cache? Now you must have studied cache replacement algorithms as well in computer organization. That means, let's say I cache a content, But you see, over the period of time, that content, let's say it is popular at current time instant, but it is after some time instant, it is no more popular, right? So therefore, it is of no use to keep that particular content cached at a particular device, right? So there has to be some kind of intelligent cache replacement policy also, right? So that will answer my question, how to cache, right? So my caching should not be a static. That means once I cache, it remains there forever, right? No. So I have to continuously learn, or I have to continuously understand which contents are important to be cached, and accordingly I have to replace the contents, right? So this is a very important graph which shows the viewing amount. So this a certain paper has that the popularity of the video, right? Video popularity has a Zipf's distribution, right? So you can see here the graph here, that is the green one shows the popularity, and the red dashed line shows the viewing amount, right? So you can see that at this point, these are the highly popular you know contents, and these are watched most of the time, whereas there is a sudden fall in the popularity, after a certain number of videos, right? So this is called the zero of the power law distributions, right? I will straight away go to some projects which may be helpful for you. So these are the different projects that are currently running, which are very, very relevant to edge caching and edge computing. Okay, so we have the Akrana project, which is a set of open infrastructure for application blueprints for edge spanning. Then you have the Kube Edge, the COD. What I would like to mention here is the Edge WorkX, right? So this is a device, right? So this is a device which is an intelligent surveillance device, right? So this actually surveys the video, right? Captures the video, and then it detects different kinds of environment, objects, people, events, incidences, etc. Right? So you can look at this project, right? So it's named as Edge WorkX. Okay. So these are some of the summary of the projects. Okay. So finally, I will conclude with some of the open issues. That means what still we can do with respect to edge computing and edge caching, right? So some of the important questions are, how do we acquire individual application requirements? So an important question is, how do we measure what are the application requirements? So there can be different application requirements. For example, live surveillance can have different requirements. Online meeting can have different requirements. Online gaming can have different requirements. Okay, so each application has different requirements, right? So we cannot do, we cannot make a same policy for all kinds of applications, right? So that's a very important question to be asked. Now, traffic management, end-to-end traffic management is again very important. Why? Because backhaul bandwidth is limited. Okay, so that's a very important question, right? And what measures need to be needed for smart decisions? Efficient management of resources, again, efficient management of resources and the network resources. Heterogeneity of edge devices. So this is a very important thing again. So the edge devices are not homogeneous. That means they may not have same storage, they may not have same computing capabilities. Different edge devices are different. So how to distribute the task, how to distribute the computing to different devices is a very important thing, right? So the devices which have higher capability may be given a higher task or higher, larger data to handle. Devices which have smaller capability may be given smaller. So this is very, very important thing to consider. Then handling the streaming data, right? So historical data along with streaming data, right? So how do we combine these two to make intelligent decisions? Then user context, right? So that means what are the type of users who are viewing this, right? So this is the some kind of teenage people, and old people, right? So different kinds of users will have different kinds of requirements. And then of course security, privacy, and trust is an important thing. As I said, edge cannot replace cloud, right? So there has to be a perfect collision, right? Because of the limitations of edge devices in terms of storage and computing. Okay, but at the same time it can provide improved services to all the users, right? So with that I conclude, and I'm open to questions.
Thank you. Thank you so much, Dr. Batabiel, for this wonderful talk. All of us, I hope, learned a lot, and I personally have also learned quite a lot from your interesting talk. Before opening up to questions, sheet has been shared in the chat box. So all of our audience who have yet not filled the attendance sheet, I request everyone to please go to the chat box. You'll find the link to the attendance sheet there. Finally, we are now open to some Q&A session. Anyone wants to ask any question, he or she can unmute himself and ask, or then else type in the chat box.
I have a question. So,
Yeah, yeah, sure.
yeah. So, for intelligent edge devices, if we are deploying some AI, that would also require some data in terms of the model parameters. How is the trade-off in terms of data and speed in that case, or is it very negligible?
Yeah. So two things there. One is the amount of AI models. For example, it can be some kind of CNN models, right? So there may be number of layers in a CNN model, right? So now, of course, as you keep on increasing the number of layers, of course, your computation resources that will right. Again, there's a trade-off. That means improved AI, right? Improved models will require large amount of data, but will provide a better outcome, right? Improved decision making, improved detection, right? So there's a trade-off between the amount of computation resources you can put at the edge device and the AI models which you put on that edge device. Okay? So currently, number of work is going on how to prune a certain AI model, depending upon specific to an application. Pruning, right? So you understand pruning, that layers or which nodes are important and which nodes or which layers are not important. So given the application, if we can reduce the AI size, or if we can reduce the model size, that will give us a better result even if we have and on specific if which kind of models, that will of course give us a better result compared to if we deploy a very large AI model without working on it.
Understood, sir. Thank you.
Thank you, Swaminathan. Anyone
Hello,
else has any question? Yes, go
hello,
ahead.
hello.
Yes, yes, you're audible. Go ahead.
Sir, I have a question.
Yes, please go on.
Sir, in the age if we implement uh, uh, that means machine learning algorithm, in that case for the video data, the lots of data, and that means lots of bandwidth are used. So, so again, that is the issue of signal. So, what solution for that?
um, no so now there are two things when we are talking of an edge device. So there can be some kind of incoming data, and there can be some kind of outgoing data. Okay. Now different applications will have different priorities of incoming data and outgoing data, right? Let's say if I have some IoT application, right? So there are millions and millions of data that is coming in to the edge device, and we have to process that data. So in that case, my network bandwidth will be very, very important for the incoming data, right? It will not be very important for outgoing data. Okay. On the other hand, if I have some surveillance camera, right, where we are collecting the data from, let's say, roadsides, we are processing it, and then we are sending it to some nearby kiosk. In that case, our
Yes.
outgoing data will be important. That means how much of data we are sending to the nearby kiosk. Okay. Now,
Yes.
depending upon the application, how do we manage the incoming data and how do we manage the outgoing data, is there is a trade-off. In case of IoT, in case of IoT, uh, we do not have much control over incoming data for an edge device, right? Because the IoT devices, they do not have a visibility where the data is getting processed. Okay, so they will keep on continuously sending a large amount of data to the edge device. Now it is up to the edge device how it manages the incoming data. So if it has a significant processing capability, then it can easily handle, and of course the outcome or the processing delay will be smaller. But if it doesn't have a significant computation resource, that means it doesn't have a very good processor, it doesn't have good processing capabilities, then the delay for processing will be higher. In case of surveillance, the edge device has a sufficient hold of what is my outgoing data, right? So in that case, it has control over how much bandwidth it can do. For example, in case of video surveillance, if I'm able to detect only the important events, I send only the important events to a nearby kiosk. I do not send the entire video, right? I send only very small parts of the video, so that will consume less bandwidth. Okay,
Yes.
so that is how an edge device. So edge device is very important for in terms of computation. Can easily control how much outgoing data can, but it doesn't have a very good control over incoming data.
Okay.
Thank you, sir. So, anyone else has any question? Uh, if no, sir, maybe I can ask a small question
Yes,
myself.
sure.
Okay. So, so you spoke about edge, and in one of the slides, or perhaps two or three of the slides, fog was also written. So, is edge an implementation of the fog, or fog an implementation of the edge,
No, yeah.
or they are related? And what are the how do we physically envision edge and fog? Like,
Yes, if I can go back to the slide. So basically, when we talk about edge, whatever is not core, generally, there is a controversy over this, but generally what most of the researchers they want to say is whatever is not core is an edge. Okay. So as I said, there are different parts of a network, right? We have the core network, and then we have the non-core network. So whatever is not core is an edge. Now fog, MEC, and cloudlet, these are again different subcategories of an edge. So you can consider edge as a superclass, and then under the edge you can have a fog, right? You can have an MEC and a cloudlet. So if you look into this device, you will get a better picture. So this is my cloud. So this is my core part, right? My cloud or the data center, this is my core. And these three are the non-core parts. So the first layer after the core is the fog layer, where we'll have different routers, the core routers, right? The non-core routers, right? The backhaul routers. Then we'll have the edge layer, which is basically my edge gateway. Okay, and then finally we'll have the edge devices. So these can be my cloud, my cloudlet. This can be my edge, and this can be my fog, and this is my cloud. Okay. So if you look at these definitions, so cloudlet is treated as a data center in a box running in a virtual machine capable of provisioning resources to end devices and users in a real time over WLAN network, right? So typically it may be inside a campus or inside an enterprise network. Whatever you run as a virtual data center is called a cloudlet, right? But it is inside a network, not in the core network. Okay. Whereas MEC is typically your radio access network, or it is a simple Wi-Fi device that is co-located with some kind of base station. So that is called the MEC, right? And um, a layer which immediately comes after your core network is denoted as the fog network, your fog layer, right? So it typically includes your routers, switches, right? Some kind of IoT gateways, etc.
Understood, sir. Thank you so much, sir. So, yeah, I hope there are no more questions. And yeah, so we are at the end of our session today. On behalf of IEEE CSSBC, I would like to thank all of you once again, and specifically Professor Butterbell for finding his valuable time to come to this session and present this wonderful talk. Sir, if I can request you to please stop sharing your screen, I have
Yes.
something to share. Yeah. Okay. Just a minute. Uh, sir, on behalf of our SBC, this is a token of appreciation, a virtual token of appreciation, come memento that we would like
Thank
to
you.
present to you. We are honored to have you today, and once again, thank you very much for giving this wonderful talk. And as a last activity of our session, I would like to request everyone who is present here, if it is possible, to please turn on your cameras. Okay, we will take a group screenshot of this event, and that will conclude basically. So, all those who, if it is possible, please turn on your cameras for some time. We will take a group screenshot. Okay, we'll just wait few seconds. Thank you, everyone. So have a very good night, and bye bye.